Good morning, good afternoon. जिथे जो है वो greeting accept करियो, and I think it's kind of a good afternoon for me. It's around 2 o'clock here in Roseville, California, and we are reading a book. We are on a third chapter, Mathematics and Reality. And first topic of that chapter is the land of Tor-Bled Nam. Let us imagine that we have been traveling on a great journey to some far off world. We shall call this word Tor-Bled Nam. I think we should come to know about that name later in the chapter. Our remote sensing device has picked up a signal which is now displayed on a screen in front of us. The images comes into the focus and we see there is a picture of a strange world. If you have a book, you should have in front of you. It's a kind of a scale. If you imagine there's an x-axis and there are strange signals on it. There is a circle and there is an apple kind of a shaped over there, and it has attached some pretty small electronic bombs, I would say. Anyhow, this is a great picture over there. So it says figure 3.1, the first glimpse of a strange world. What can it be? Is it some strange looking insect? Perhaps instead it is a dark colored lake with many mountain streams entering it. Or could it be some vast or oddly shaped alien city, with roads going off in various directions to small towns and villages nearby? Maybe it is an island, and then let us try to find whether there is a nearby continent with which it is associated. This we can do by backing away, reducing the magnification of our sensing device by a linear factor of about 15. Lo and behold, the entire world springs into the view. There is another picture now, so kind of a backing away, figure 3.2 in the book, Tor-Bled Nam in its entirety, the location of magnifications shown. Okay, figure 3.1, 3.3, 3.4. Okay, our island is seen as a small dot indicated in figures, and in figures 3.1 and 3.2, basically the filaments, streams, roads, bridges from the original island all come to an end, with the exception of one attached at the inside of its right hand crevice, which finally joins on to the very much larger object that we see depicted in figure 3.2. This larger object is clearly similar to the island that we saw first, though it is not precisely the same. If we focus more closely on what appears to be the object's coastline, we see innumerable protuber instances, roundish, but themselves possessing similar protuberances of their own. Each small protuberance seems to be attached to a larger one at some minute place, producing many watts upon watts. As the picture becomes clearer, we see myriads of tiny filaments emanating from the structure. The filaments themselves are forked at various places and often mended widely. At certain spots on the filaments, we seem to see little nodes of complication, which our sensing device, with its present magnification, cannot resolve. Clearly, the object is no actual island or continent, nor a landscape of any kind. Perhaps, after all, we are viewing some monstrous beetle, and at the first that we saw was one of its offspring, attached to it still by some kind of a filamentary umbilical cord. Let us try to examine the nature of one of our creature's warts by turning up the magnification of our sensing device by a linear factor of about 10. The location being indicated under figure 3.3, there is a 3.3 picture over there with more magnification. The wart itself bears a strong resemblance to the creature as a whole, except just at the point of attachments. Notice that there are various places in picture where 5 filaments come together. There is perhaps a certain 5ness about this particular wart, as there would be 3ness about the uppermost wart. Indeed, if we were to examine the next reasonable size wart a little down on the left, figure 3.2, we should find a 7ness about it, and for the next a 9ness, and so on. As we enter the crevice between the two largest regions of the figure, we find warts on the right characterized by odd numbers increasing by 2 each time. Let us peer deep down into this crevice, turning up the magnification from that of figure 3.2 by the factor of about 10 more. Okay, and we are just increasing the magnification. We see numerous other tiny warts and also much swirling activity. On the right, we can just discern some tiny spiral seahorse tails in the area we shall know as Seahorse Valley. Here we shall find, if the magnification is turned up enough, various sea anemones or regions with distinctly floral appearance. Perhaps, after all, this is indeed some exotic coastline, maybe some coral reef teeming with life of all kinds. What might have seemed to be flower would reveal, on further magnification, to be composed of myriads of tiny but incredibly complicated structures, each with numerous filaments and swirling spiral tails. So there is another device. The main crevice, Seahorse Valley, is just discernible on the lower right. Very beautiful picture over there of some kind, and they're describing it as a Seahorse Valley. Oh, okay. I thought it as a cracker, which is cracking something. Anyhow, let us examine one of the larger seahorse tails in some detail, namely the one just discernible where indicated as in those images. With a further approximate 250-fold magnification, we are presented with the spiral depicted in there is a spiral image now. They magnified it 250-fold. We find this is no ordinary tail, but is itself made up of the most complicated swirling back and forth with innumerable tiny spirals and regions like octopuses and seahorses. At many places, the structure is attached just where two spirals come together. Let us examine one of these places, increasing our magnification by a factor of about 30. Behold, do we discern a strange but now familiar object in the middle? A further increase of magnification by a factor of 6 reveals a tiny baby creature, almost identical to the entire structure we have been examining. If we look closely, we see that the filaments emanating from it differ a little from those of the main structure, and they swirl about and extend to relatively much greater distances. Yet the tiny creature itself seems to differ hardly at all from its parents, even to the extent of possessing offspring of its own in closely corresponding positions. These we could again examine if we turned up the magnification still further. The grandchildren would also resemble their common ancestor, and one rarely believes that this continues infinitely. We may explore this extraordinary world of Tor Bloodnam as long as we wish, tuning our sensing device to higher and higher degree of magnification. We find an endless variety. No two regions are precisely alike, yet there is a general flavor that we soon become accustomed to. The now familiar beetle-like creature emerged at yet tinier and tinier scales every time the neighboring filamentary structure differed from what we had seen before, and present us with fantastic new scenes of unbelievable complication. What is this strange, varied, and most wonderfully intricate land that we have stumbled upon? No doubt many readers will already know, but some will note the word is nothing but a piece of abstract mathematics, the set known as Mandelbrot set. Complicated it undoubtedly is, yet it is generated by a rule of remarkable simplicity. To explain the rule properly, I shall first need to explain what a complex number is. It is well that I do so here. We shall need complex numbers later. They are absolutely fundamental to the structure of quantum mechanics and are therefore basic to the workings of the very world in which we live. They also constitute one of the great miracles of mathematics. In order to explain what a complex number is, I shall need first to remind the reader what is meant by a term real number. It will also be helpful also to indicate the relationship between the concept and the very reality of the real world. Real numbers. Recall that the natural numbers are whole quantities 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. These are the most elementary and basic amongst the different kinds of numbers. Any type of discrete entity can be quantified by the use of natural numbers. We may speak of 27 sheep in a field, of 2 lightning flashes, 12 nights, 1000 words, 4 conversations, 0 new ideas, 1 mistake, 6 absentees, 2 changes of direction, etc. Natural numbers can be added or multiplied together to produce a new natural number. They were the objects of a general discussion of algorithms as given in the last chapter. However, some important operations may take us outside of the realm of natural numbers, the simplest being subtraction. For subtraction to be defined in a systematic way, we need negative numbers. We can set out the whole system of integers minus x, minus 5, minus 3, minus 2, 1, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, kind of a negative infinity to positive infinity. For this purpose, certain things such as electric charge, bank balances, or dates are quantified by the numbers of this kind. These numbers are still too limited in their scope. However, since we can come unstuck when we try to divide one such number by another, accordingly we shall need the fractions or rational numbers as they are called: 0, 1, minus 1, half, minus half, 2, minus 2, 3 by 2, minus 3 by 2, 1 by 3 and so on. These suffice for the operations of finite arithmetic, but for a good many purposes we need to go further than this and include infinite or limiting operations. The familiar and mathematical highly important, the quantity pi, for example, arises in many such infinite expressions. In particular, we have pi is equal to 2 curly braces, 2 by 1, 2 by 3, 4 by 3, 4 by 5, 6 by 5, 6 by 7, 8 by 7, 8 by 9 and so on, and pi is equal to 4 bracket 1 minus 1 by 3 plus 1 plus 5 minus 1 by 7 plus 1 by 9 minus 1 by 11 plus so on. These are famous expressions, the first having been found by the English mathematician, grammarian and cipher expert John Wallis in 1655, and the second in fact by a Scottish mathematician and astronomer and inventor of the first reflecting telescope, James Gregory, in 1671. As with the pi numbers defined in this way, we need not to be rational, that is not of the form of n by m, where n and m are integers with m non-zero. The number system needs to be extended in order that such quantities can be included. This extended number system is referred to as system of real numbers, those familiar numbers which can be represented as infinite decimal expansions, such as minus 583.7026443912100, 9538, and so on. In terms of such a representation, we shall have a well-known expression of pi, which is pi is equal to 3.14159265358979323846. Among the types of numbers that can be represented in this way are the square roots or cube roots or fourth roots, etc. of positive rational numbers, such as square root of pi is equal to 1.4142 and so on, or indeed the square root of any positive real number, as with the expression of pi found by great Swiss mathematician Leonhard Euler. Pi is equal to square root of curly braces 6 bracket 1 plus 1 by 4 plus 1 by 9 plus 1 by 25 plus 1 by 36 plus so on. Real numbers are in fact the familiar kinds of numbers that we have to deal with in everyday life, although normally we are concerned merely with approximations to such numbers and are happy to work with expansion involving only a small number of decimal places. In mathematical statements, however, real numbers may need to be specified exactly, and we require some sort of infinite description, such as an entire infinite decimal expansion, or perhaps some other infinite mathematical expression, such as the above formula of pi given by Wallace, Gregory, and Euler. I shall normally use decimal expansions in my description here, but only because these are most familiar to a mathematician. There are various rather more satisfactory ways of presenting real numbers, but shall we not need to worry about this here. It might be felt that it is impossible to contemplate an entire infinite expansion, but this is not so. A simple example where one clearly can contemplate the entire sequence is 1 by 3 is equal to 0.33333, where the dots indicates us to the succession of threes carries or on indefinitely. To contemplate this expansion, all we need to know is that the expansion does indeed continue in the same way indefinitely with threes. Every rational number has a repeated decimal expansion, such as 93 by 74 is equal to 1.2467567567567567, where the sequence 567 is repeated indefinitely, and this can also be contemplated in its entirety. Also, the expression 0.222000222222000000000000, which defines an irrational number, can certainly be contemplated in its entirety. The strings of zeros and twos simply increasing in length by 1 each time. And many similar examples can be given. In each case, we shall be satisfied when we know a rule according to which the expansion is constructed. If there is some algorithm which generates the successive digits, then the knowledge of algorithm provides us with a way of contemplating the entire infinite decimal expansion. Real numbers whose expansions can be generated by algorithms are called computable numbers. The use of a denary rather than say a binary expansion has also no significance. The numbers which are computable in this sense are just the same numbers whichever base for an expansion is used. The real numbers pi and square root of 2 that we have just seen considering are examples of computable numbers. In each case, the rule would be a little complicated to state in detail, but not hard in principle. However, there are also many real numbers which are not computable in this sense. We have seen in the last chapter that there are non-computable sequences which are nevertheless perfectly well defined. For example, we could take the decimal expansion whose nth digit is 1 or 0, according whether or not the nth Turing machine acting on a number n stops or does not stop. Generally, for a real number, we just ask that there should be some infinite decimal expansion. We do not ask that there should be an algorithm for generating the nth digit, nor even that we should be aware of any kind of rule which in principle defines what the nth digit actually is. Computable numbers are awkward things to work with. One cannot keep all one's operationals computable, even when one works just with the computable numbers. For example, it is not even a computable matter to decide in general whether two computable numbers are equal to one another or not. For this kind of reason, we prefer to work instead with all real numbers where the decimal expansion can be anything at all and need not to just be, say, a computable sequence. Finally, I should point out that there is an identification between a real number whose decimal expansion ends with an infinite succession of nines and one whose expansion ends with an infinite succession of zeros. For example, minus 27.186099999 is equal to minus 27.186100000. Next topic is how many real numbers are there. Let us pause for a moment to appreciate the vastness of generalization that has been achieved in moving from rational numbers to the real numbers. One might think at first the numbers of integers are already greater than the number of natural numbers, since every natural number is an integer, whereas some integers, namely the negative ones, are not natural numbers. And similarly, one might think that the numbers of fractions is greater than the number of integers. However, this is not the case, according to the powerful and beautiful theory of infinite numbers put forward in the late 1800s by the highly original Russian-German mathematician George Cantor. The total number of fractions, the total number of integers, and the total number of natural numbers are all the same infinite number, denoted by Aleph naught. There is a sign Aleph naught. Remarkably, this kind of idea had been partly anticipated some 250 years before in the early 1600s by the great Italian physicist and astronomer Galileo Galilei. We shall be reminded of some of the Galileo's other achievements in chapter 5. One may see that the numbers of integers is the same as the number of natural numbers by setting up one-to-one correspondence as follows. Integer 0, natural number 0, minus negative integer 1 is equal to natural number 1. 1 is 2, negative 2 is 3, 2 is 4, negative 3 is 5, 3 is 6, negative 4 is 7, negative n is 2n minus 1 in natural number, n integer is 2n in natural number, and so on. Note that each integer and each natural number occurs once and once only in the list. The existence of one-to-one correspondence like is what, in Cantor's theory, established that the number of objects in the left-hand column is the same as the number of objects in the right hand column, that is integers and natural numbers. Thus the numbers of integers are indeed the same as the number of natural numbers. In this case the number is infinite, but no matter the only peculiarity that occurs with infinite numbers is that we can leave out some of the members of one list and still find a one-to-one correspondence between the two lists. In a similar but somewhat more complicated way, we can set up one-to-one correspondence between the fractions and integers. For this, we can adapt one of the ways of representing pair of natural numbers, the numerators and denominators, as single natural numbers. Sets that can be put into one-to-one correspondence with the natural numbers are called countable. So the countable infinite sets are those with Aleph naught elements. We have now seen that the integers are countable, and so also are all fractions. Are there sets which are not countable? Although we have extended the system in passing from natural numbers to first of the integers and then the irrational numbers, we have not actually increased the total number of objects that we have to work with. We have seen the net numbers of objects is actually countable in each case. Perhaps the reader has indeed got the impression by now that all infinite sets are countable. Not so, for the situation is very different in passing to two other real numbers. It was one of the Cantor's remarkable achievements to show that there are actually more real numbers than rationals. The argument that Cantor used in the diagonal slash that was referred in chapter 2 and that Turing adapted in his argument to show that the halting problem for Turing machines is unsoluble. Cantor's argument, like Turing's later one, proceeds by reductio and absurdum ad absurdum. Suppose that the result we are trying to establish is false, that is, all the set of real numbers is countable, then the real numbers between 0 and 1 are certainly countable. We shall have some list providing to one-to-one pairing of such numbers with the natural numbers, such as natural number 0 is 0.10335679, 1 is 0.143, 2 is 0.21660952133, 3 is 0.4305357779, and so on, and they have a diagonal representation of it too. So I have marked out the diagonal digits in bold type. These digits are for this particular listing are 14100314851, and the diagonal slash procedure is to construct a real number between 0 and 1 whose decimal expansions differ from these digits in each corresponding place. For definiteness, let us say that the digit is to be 1 whenever the diagonal digit is different from 1, and is 2 whenever the diagonal digit is 1. Thus, in this case, we get the real number 0.21211121112. This real number cannot appear in our listing since it differs from the first number in the first decimal place, from the second number in the second place, from the third number in the third place, etc. This is a contradiction because our list was supposed to contain all the real numbers between 0 and 1. This contradiction establishes what we are trying to prove, namely that there is no one-to-one correspondence between the real numbers and the natural numbers, and then accordingly the number of real numbers is actually greater than the number of rational numbers and is not countable. The number of real numbers is the infinite number labeled C. C stands for continuum, another name for the system of real numbers. One might ask why this number is not called what is that expression called as? It is not alpha naught 1. Say, in fact, the number alpha naught 1 stands for the next infinite number greater than alpha naught 0, and is a famous unsolved problem to decide whether in the fact C is equal to alpha naught 1, and so-called continuum hypothesis. It may be remarked that the computable numbers on the other hand are countable. To count them, we just list in numerical order those Turing machines which generate real numbers. We may wish to strike from the list of any Turing machines which generates a real number that has already appeared earlier in the list. Since the Turing machines are countable, it must certainly be the case that the computable real numbers are countable. Why can we not use the diagonal slash on the list and produce a new computable number which is not on the list? The answer lies in the fact that we cannot computably decide in general whether or not a Turing machine should actually be in the list, for to do so would in fact involve being able to solve the halting problem. Some Turing machines may start to produce the digits of a real number and then get stuck and never again produce another digit because it doesn't stop. There is no computable means of deciding which Turing machines will get stuck in this way. This is basically the halting problem. Thus, while our diagonal procedure will produce some real number, that number will not be a computable number. In fact, this argument could have been used to show that the existence of non-computable numbers. Turing's argument to show that the existence of classes of problems which cannot be solved algorithmically, as was recounted in last chapter, follows this line of reasoning. We shall see the other applications of the diagonal slash later. So our next topic is reality of real numbers. On page number 86, we shall continue from here. Thank you for watching.